Hello everyone, my name is Muhammad Abdul Nabi and I'm currently a master's student studying computer science at the University of Oklahoma. My academic research has been around machine learning, dimensional reduction, and large language models. And I've also gotten a chance to explore RAG and a little bit of graph analytics. I participated in this hackathon because I saw an opportunity to combine my experience in RAG architecture with GPU accelerated graph analytics to solve real business problems. I believe that the intersection of these technologies is particularly exciting as it allows us to extract actionable insights from complex relational data at scale. Today I'll be presenting GraphCatalyst, a platform that leverages GPU acceleration to show us deeper insights from e-commerce product networks through natural language queries. So for GraphCatalyst, I chose the Amazon product co-purchasing dataset, and it was downloaded from Stanford Snap. This dataset represents Amazon's customers who bought this item also bought feature. It contains over 400,000 products and 3.3 million co-purchasing relationship. So here we download the dataset, and we have the dataset here in .txt format. Then we're loading this dataset. So first we're creating a network X graph, which will later we convert it to cuGraph. So yeah, we loaded it here. And I actually want to talk about the business challenge here. So e-commerce platforms, they have massive product networks where understanding this relationship between products directly impacts their revenue. Through recommendations, cross-selling, and inventory planning, traditional CPU-based analysis of these networks at this scale is very slow and would require expensive computational resources. And that's what GraphCatalyst is trying to address. Basically addressing three key business needs: identifying influential products that drive purchasing behavior, detecting natural product communities for category optimization, and generating personalized recommendation strategies in real time. So I want to also talk about another thing. This function here, so we're also creating a cuGraph. We have this function right here. I want to say that we create a directed graph where nodes represent products and edges represent co-purchasing relationship. This direction is very important because if customers who buy product A also buy product B, the reverse isn't necessarily true. So to handle this dataset scale, I implemented optimization techniques including batch processing and optional sampling for development. And the final graph construction will contain this number right here, over 400,000 nodes and over 3 million edges. So I have some plots that I want to go over. So first is the Amazon product network matrix. These charts reveal the networks over a structure. We can see that the degree distribution follows a power law, typical of scale-free networks. The page rank distribution shows influence. It's concentrated in a relatively small number of products, and these bottom chart right here, they identify the most central products by in degree and also by page rank, which are prime candidate for promotional activities. The next plot I want to go over is Amazon product network sample, and here we have force directed layout of our product network sample. The red dots represent highly influential products with high page rank score, and if you notice right here as well how several clusters are naturally representing distinct product communities, the connections between clusters represent bridge products that span multiple categories, and these are strategic products for cross-selling initiatives. Another visualization as well that I want to go over is the communities plots, which is right here. So we have the product communities by size, and for now we just have this symbol of communities. In the dataset we have more communities. Actually, we have around 157 communities, and we're using the Louvain algorithm to detect these communities. And here's the product groups, and we also have the community cohesion matrix, and these charts, they show the community density and clustering coefficient. For example, community 2 here has the highest density, meaning products within this community are tightly interconnected. Higher clustering coefficient indicate more complete interconnections within the communities, and these are valuable for bundling opportunities. So in this code here, we're setting up OrganoDB interface, and also this is a persistence code. So we're establishing the cloud connections, and we're connecting to the OrganoDB cloud. Here's just some code for connection, and we're doing the persistence here involving inserting the product nodes and also adding pre-computed analytics such as PageRank and centrality matrix. We also creating co-purchasing relationship edges, and we're storing the community detection results. So after creating all the tools in OrganoDB, actually the core innovation here is Agentic App architecture. It implements what I would call dual query execution using LangChain and custom tools. So for simple queries like find products similar to product X, the agent routes the request to OrganoDB tools, which effectively traverse the graph and returns the results. For complex analytics like find the most influential products or detect product communities, the agent leverages our GPU accelerated analytics pipeline using the cuGraph. The system also handles hybrid queries such as that also combines both approaches. So for instance, what are the most influential products in community X? First, the query identifies the products in this community, which is the reversal problem, and then ranking them by influence. So actually, to go quickly and show you some live demo, I have some queries here that we could run. You can explore more of the code in the notebook, but for instance, query 0, which is what are the top 5 most influential products in the network. You see here it returns the products with PageRank and in degree scores, and then query 1 find products similar to product 1, and then it will find 10 products that are similar to product 1. Query 2, and again it's using cuGraph. This one is for community detection, so we're asking which product communities exist in the network. So yeah, this one is creating the cuGraph from the network X graph. It created it with this number of vertices and edges, and it's able to define these communities, and then running query 3, recommend complementary products for product 10. Query 4, we are trying to analyze product 5 comprehensively. We also have another query for identifying the shortest path, and also cross selling strategies. So this one, if we want to know the shortest path between two products, and this query is for cross-selling strategies. So we having the product profile, so we can define whatever product we want here. I can change this one to product 100, for instance. Again, it's creating a product profile, and